Welcome to Lecture 5 for Chemistry 418, Radiochemistry. This lecture is on beta decay. The readings for Lecture 5 are Chapter 3 from Nuclear Radiochemistry and Chapter 8 from Modern Nuclear Chemistry. This chapter is going to cover the neutrino hypothesis. We're going to talk about spectral shape and what information can be derived from that. We're going to introduce something called Kurie plots, which is a way of evaluating data to understand what sort of transitions occur. We're going to talk about equations that are used to derive the beta decay rate constants. We can use this information, since a rate constant can be measured, to understand some of the properties of the isotope undergoing decay. We're going to discuss selection rules, which are based upon the spin and parity change from the parent to the progeny nuclear state, which may be an excited nuclear state. Then we're going to talk about different types of transitions. The majority of radioactive nuclei are outside the range of alpha decay. Beta decay is a dominant form of decay for radioactive isotopes. It was the second particle that was found after alpha decay, hence beta. It's a negative particle. It has a distribution of energies. Unlike alpha, where you would see peaks, beta decay energies would be a distribution. There's also another particle that's necessary to balance the spin. There's a parent progeny and an electron. You need to account for a half integer spin somewhere. This is part of the driving factor for the neutrino hypothesis. In beta decay, A remains unchanged, but Z changes. For beta decay, electron capture, and positron decay, we get different changes in the Z. For beta minus decay, where an electron is emitted, a neutron is converted to a proton. For electron capture and positron decay, a proton is converted into a neutron. So for beta minus decay, elements move up the periodic table. Electron capture and positron decay, they move down the periodic table. As we can see, there's examples of beta minus decay, electron capture. Beta minus decay, we're increasing the proton number. A remains the same. For electron capture and beta minus decay, we're decreasing the proton number. A remains the same. The half-lives for beta decays are from a few milliseconds to 10 to the 14th years. You can see that this is a little bit different than the range for alpha decay. Alpha decay half-lives can be shorter than milliseconds. On a subatomic level, we could think of beta decay involving a few mechanisms. For instance, here's a neutron that's composed of 1 up, 2 down quarks. It gets converted into a proton, where one of these down quarks gets converted to an up quark, with the emission of a W- boson, and this W- boson subsequently decays into the electron and the antineutrino. This is actually the electron antineutrino, but for this lecture, we'll just call it the antineutrino.
We can review what we know about Q-value calculations as we discussed earlier for beta decay. As an example, this is something we've already shown. We talk about the energy related from beta decay. So for emission of an electron, where we go from a Z to Z plus 1, the Q value is equal to the mass difference between
the parent and the progeny,
as listed here. And this is an example for the beta decay of sodium-24. We can also do the same thing for electron capture of sodium-22. And if we see here the electron capture, it's just, again, the difference between the
parent and the progeny.
For positron decay, which we're not going to give an example of, but we've given an example earlier for the Q value, we need to include 2 electron mass. Similar to alpha decay, there's systematic variations with beta decay energy and half-life. This is shown by the mass parabola here, where we see that there's this larger energy change as we go from more unstable to more stable beta isotopes. However, unlike alpha decay with the Geiger-Nuttall equation, there's not as strong a relationship, this linear relationship, as what's observed with alpha decay. And what we're going to see is that beta decay half-lives really depend upon variations in spin and parity. Now, there are some trends that we can observe for beta stable nuclei. We look at a mass parabola for this odd A135. For most odd A isotopes, there's one beta stable nuclei. And if we look here, this is the barium-135, which is the most stable, sits at the bottom of this mass parabola. However, for even A, you can have up to 3 beta stable nuclei, and you can evaluate this by inspection from the chart of the nuclides. Some odd nuclei near the stability valley, for example, copper-64, can decay in both directions. As we see with copper-64, it has a beta minus and a beta plus positron emission. So both these form even nuclei. That's one of the reasons that you can drive this stability. And also, as we already discussed in the previous slide, beta particle energy is not discrete. There's a continuum of energy. And as we look here, you can find an electron emitted from the nucleus from a range of energies, and the same thing with the positron emitted from the nucleus for this copper-64 decay. This is unlike alpha decay, where you get very discrete energies. Now we can use this energy decay behavior to evaluate some properties associated with the decay, and one of the first things that we can come up with is to discuss the neutrino. The neutrino solves some of the problems associated with beta minus decay. So there's a continuum of electron emission energies. Well, that means that the total energy must be the sum of a number of particles. Also, there's a zero charge problem. For instance, if I convert a neutron into a proton and an electron, I have charge balance. So whatever this particle is that is taking away some of the energy, so the electron that's emitted can have a range of energies, it can't have a charge. It also has a very small mass, because we see that the electron energy that's emitted from beta decay can actually go up to the Q value. So when we say small mass, we also mean possibly no mass. And it needs to be an antiparticle, because we are creating a particle, an electron, so we need to create some antimatter. And it needs to obey Fermi statistics. It has a spin of 1/2. This is so that we can couple the initial and final states. We need to balance this reaction of a neutron to a proton plus an electron. It's not spin balanced. We need to have another spin associated with it. And this is where we get these behaviors that Fermi described as the neutrino. So it's small mass, zero charge, and obeys Fermi statistics. One of the properties of this small rest mass of the neutrino is that it's very difficult to detect. Two current routes that are used to detect neutrinos through inverse beta decay are listed here, where the reaction of a neutrino on chlorine-37 makes argon-37, which this is radioactive and this is decayed. And then the gallium going to germanium, going back to the gallium from the germanium decay. Both these are used in neutrino detectors. Now, antineutrinos are emitted in beta minus decay, and neutrinos, since it's matter, are emitted in positron decay, since positron is antimatter. And these neutrinos are created at the moment of emission. So the reaction here for a neutron going to a proton, an electron, and an antineutrino, and a proton going to a neutron, a positron, and a neutrino. The spins of these neutrinos are involved in assigning decay, so they can have either spin up or spin down properties. The electron and neutrino spin can be aligned or anti-aligned during decay. So if they're aligned, if they're parallel, the spins will sum up. The spin change will be on the order of 1, either +1 or -1. If they're anti-parallel, they cancel, the spin change will be 0. So there's two possible alignments for creative spins. One is Fermi, where the spin change is 0. These are dominant at low A isotopes, and Gamow-Teller, where the spin change is 1. And these tend to be observed at higher A. If we examine low A isotopes, the number of protons is approximately equal to the number of neutrons. So if I swap a neutron to a proton state or a proton to a neutron state in the shell model, which we'll describe later, the occupied states are going to be about the same. The overall spin change will be 0. This isn't true for Gamow-Teller, where as I go higher in A, I tend to have more neutrons than protons. So if I take a neutron and convert it to a proton state, that spin change will be non-zero, and it tend to be on the order of 1. Sources can have a mixture of Fermi and Gamow-Teller spins. These spin types can be used to define the decays. For even nuclei, let's say mirror nuclei, where the number of neutrons equal the number of protons.
Neutrons and protons can be in the same shell in the shell model. Even nuclei with equal numbers of neutrons and protons are by definition only available in the light isotopes.
I can get transitions from 0 plus to 0 plus decay that can take place by a Fermi transition. These heavy nucleons, the gamma Teller is the main mode, as we already discussed in the previous slide, because we need to account for the spin difference. Now, these nuclei can be rather complex, where the rate of decay depends upon the overlap of the wave functions
of the ground state of the parent and the progeny state.
This final state depends upon the decay mode. So spin and parity
changes from parent to progeny,
and the overall delta of the change, this degree of the change, is going to have an effect on the rate of decay, or as we see, the decay constants. So I can get half-life information from this. I can also use the half-life information to understand nuclear states. I can calculate the decay constant if the wave functions are known. So the initial observed rate indicates the quantum mechanical overlap of the initial and final states of the wave functions. And we'll get into this in more detail when we discuss Fermi's golden rule, where Fermi came up with an equation to describe the decay constant based upon these initial and final wave functions and their overlaps. The positron, which is emitted during positron decay, was actually postulated before it was seen. In 1931, relativistic equations could be solved for electrons with positive energy states, so basically the opposite of an electron. What also is known is that pair production, in other words, the creation of a positron-electron pair, can be performed by a photon in a nuclear field. This is one way photons interact with matter. If you have a high enough photon energy, well above 1 MeV, you can actually create an electron-positron pair. The other thing that is known is that when a positron and electron interact, there's annihilation that occurs. So there's a conversion of mass to energy when they interact, is what's shown here. And we see two photons, 511 keV, are produced and going 180 degrees from each other. Also, unlike electron capture, there is no positron capture decay. This two photon with a half an MeV creation during positron annihilation is what's used in positron emission tomography to map out three-dimensionally images, which are often used in medical applications. Beta decay can be modeled based upon the weak force. So this weak interaction is what Fermi used, and he based it upon the electromagnetic theory for light emission. And fundamentally, you have fermions are interacting during the reaction. An example is shown here, example of a neutron going to proton, electron, antineutrino. And this degree of interaction can actually be evaluated by something called the Fermi constant. And this Fermi constant, G, is something that's determined by experiment. It's about 10 to the minus 3 of an electromagnetic force, and it plugs into an equation which is used to determine the emitted electron momentum range per unit time. This winds up being spectral information, so we can get information about the decay spectra of electrons from this term, and we'll describe this equation. Now, this weak interaction equation that's shown here has a number of different components to it, and it fundamentally gives the probability of an electron with a momentum, gives a momentum spectra, and we can convert this into an energy spectrum. Some of the terms that are involved with this is the electron wave function, shown here, the neutrino wave function, shown here, and if I take the square root of the absolute values, I can use this to determine the probability of finding the electron and the neutrino at the nucleus. We also have something called the matrix element, which is shown here. This characterizes the transition from the initial to the final nuclear state. If I take the absolute value, the square of that, it's a measure of the overlap between the wave functions of the initial and final states. So from this equation, I can use the spectral shape, and here spectral momentum, and information about the electron and neutrino wave function to determine something about this matrix element, which gives me an overlap information. Now, if I integrate this equation down here, over all possible energies or momenta from 0 to the maximum, it should be able to provide some probability or a lifetime. Now there's variations in the number of electrons at any given energy, and I can use this to derive the emission spectra. We'll see where that's not 100% true. And I can use this for a calculation of the decay constant. Now, classically allowed transitions, in other words, where I have 0 orbital angular momentum change, those that have s orbitals are allowed transitions. Now, there's higher probabilities for locating the electron and neutrino at the nucleus for the s wave function compared to the higher L wave function, so P, D, F, etc. These can be observed, but they won't be as allowed as the S wave function. So we're going to call these forbidden first, second, third, etc., forbidden transition. And what we're going to see is that if I take the transition elements, they're going to be larger than the forbidden elements. So the magnitude of the neutrino wave function and this matrix mixing element are independent of energy divisions between the electron and the neutrino. Those are some of the parameters for this equation. The spectrum shape can be determined entirely from information related to the electron and the density of states. We're going to use that to get our typical bell-shaped curve. This is for energy. The one we showed earlier was for momentum. However, this equation does neglect the Coulomb interactions between the nucleus and the emitted either electron or positron. This is a reasonable assumption for low z. However, at high z, it's not true. The nucleus will have an impact on the energy of the particle emitted from the nucleus. There's also another equation, which is listed here, for a density of states as a function of energy, where we talk about the total energy of the system, where that's the kinetic energy plus the rest energy. So we use the kinetic energy, a rest energy of 1, and then the kinetic energy included goes to some maximum value. We can solve for this equation, and we can also get the characteristic bell-shaped beta spectrum. This Coulomb correction, as we already discussed, at low z, there really isn't as large of a Coulomb perturbation on the behavior of the emitted particle. However, at higher z, this effect needs to be taken into account. And what we generally see is the electron spectra has more low-energy particles, so it's shown here. The positron spectra has fewer low-energy particles or more high-energy particles. And if you think about this, this is because I have a positive positron being accelerated away from a positive nuclear charge. Now I can treat this Coulomb correction as a perturbation. This perturbation is also called the Fermi function, and it's defined as the ratio of the electron wave function, so the probability to find the electron with the Coulomb versus over the same probability without the Coulomb. And this perturbation on the wave function, the spectrum can be multiplied by this Fermi function to account for the Coulomb correction. And that equation is shown here, where I have certain terms such as
z of the progeny nucleus,
the beta particle velocity, and positive for electrons and negative for positrons. There's also another measure of comparing theory and experiment for momentum measurements, and that's called the Kurie plot. And we're going to briefly describe this, but it's fundamentally the square root of the number of beta particles within a given range divided by the Fermi function, and I plot that against this whole beta particle energy. If the relationship is linear, such as here, that's going to be an allowed transition. If it's nonlinear, that's going to be a forbidden transition. The other thing that's an observation of the Kurie plot is that the x-intercept winds up being the Q value for the decay. Now, as we described earlier, all these models can be used to evaluate a transition probability, and this is called Fermi's golden rule. So we can treat the beta decay as a transition that depends upon the strength of coupling between the initials and final states. If that strength of coupling is high, the transition probability is high. If it's low, the transition probability is low. So from Fermi's golden rule, we have this equation here where the decay constant is equal to 2 pi divided by h bar, this matrix element, and a density of states that are available to the system after transition. Higher the density of states, more states available, the higher the probability will be this transition. So this matrix element, this density of states, it's just wave functions of the initial and final state, and this operator here, which couples the initial and final state. Fundamentally, the rate can be proportional to the strength of coupling between the initial and final states, and includes this density of states. So the final state can be composed of several states with the same energy. And this is classic in quantum mechanics. These are called degenerate states. So states with the same energy. So if I have a number of states with the same energy, that's going to improve the probability of decay. We can use this information to develop something called comparative half-lives. This is based upon the probability of an electron energy emission coupled with the spectrum and Coulomb correction. And we're going to call this Ft, or F naught T1 half. This is basically a comparative half-life for a transition, where our decay constant is equal to log 2 divided by 1 half is equal to K, our matrix element, and this F term. Our K term, well, that's a mixture of a number of constants and a Fermi term, and this F naught state is an integration of all the energy states that are possible for this decay. This assumes that the matrix element is independent of energy, because we're not changing it as this energy changes, which is true for allowed transitions, not necessarily true for forbidden transitions. So we can look at this Ft, or F naught T1 half. It's a comparative half-life, and this could be thought as a half-life corrected for differences in Z, right, which accounts for a Coulomb behavior, and W, which is the total kinetic energy. There's a rapid way for estimating Ft and energy.
We will go over some equations that can be used to determine the log Ft for beta minus decay, positron decay, and electron capture. Additionally, there is a website where the URL is shown here from Brookhaven National Laboratory for inputting data and evaluating the log Ft values for the different beta decays.
Fundamentally, the log Ft is equal to log F plus log T1 half. T1 half needs to be in seconds. There's ways of calculating these log F values. We showed an integration on the previous slide. Here we're going to have 3 equations that are listed here for beta minus, positron, and electron capture, where all these equations are going to be our functions of
the decay Q value and the Z of the progeny.
I can determine the log F value. If I get the half-life in seconds, well, the log Ft is nothing more than the log F plus the log of the half-life in seconds. By doing this, we can get a range of log Ft values that basically break decays into allowed transitions, first forbidden, second forbidden, third forbidden. I put 2 tables here that you'll find in the different textbooks that describe the ranges for the allowed and the forbidden transitions. And what we generally see is that for a given type of transition, there will be a value for a spin change and a parity change. So for instance, a first forbidden will tend to have a spin change depending upon if it's Fermi or Gamow-Teller of 1 or 2, along with the parity change. Second forbidden, 2 or 3, no parity change. Third forbidden, 3 or 4 with the parity change, etc. Now we can use these equations to calculate some log Ft values. And then let's go for the positron decay of oxygen 14 to nitrogen 14. The Q value for this reaction is 1.8 MeV, and the half-life is 70.6 seconds. If I take my positron equation here, and now I plug in my values for the decay of oxygen 14, So the Z is now the Z of nitrogen. Q value is for the E. I come up with a value of log F beta plus of 1.83. T is 70.6 seconds. Log of that is 1.84. I get a log FT value of 3.67. And that fits into a super allowed category.
On this figure, it would be between super allowed and allowed. And what we do see from the log FT value, that the transition is allowed.
We can perform another log FT calculation. Now let's use the beta decay of bismuth 212. The Q value is listed here. We need the Q value in MeV, so it's the 2.254 MeV. The half-life is 3,600 seconds. Well, we actually need to get the beta decay half-life, which winds up being 5,625 seconds. Remember that this is a 46% beta branch, so we use one of the equations that we discussed earlier. If I use my equation for the log F beta minus, I have this equation. I plug in my half-life, I plug in my Q value,
and 84 for the Z of the progeny polonium.
My log F is 3.37. My log T is 3.75. I get a log FT value of about 7.5. And I actually compare this to what's listed in the table of the isotopes. As you see here, these values here are my log FT values for the individual transitions. So this bismuth 212 going from a 1 minus state to a 0 plus state has a log FT of 7.3 listed here. We calculated to 7.5. That's a pretty good estimation. And we will see that this is a first forbidden type transition based upon the value.
Regardless if the value is 7.48 or 7.3, they would both indicate first forbidden.
So what drives these changes in these log FT values? Let's examine it for mercury 205. Here are these log FT values. What we see is that the decay in beta is really driven by the change of the spin and parity from the parent state
to the progeny state.
The lowest log FT value is for a 1/2 minus to 1/2 plus state. And we see that these transitions, if we were to try to go from a 1/2 minus to a 5/2 plus state, we have the highest log FT value, and that's driven by this overall change in spin. We could go from this 1/2 minus to this 1/2 plus state. However, the energy transition is not the greatest.
For the same spin and parity transition, the decay with the largest energy transition is often favored.
As a review of what we just gone over with the models, there are a few selection rules which are apparent in beta decay. One that's important is this Fermi or Gamow-Teller transition. So the overall spin change of being 0 Fermi or 1 Gamow-Teller. Those are your favored or allowed transitions. The Fermi occurs at low A and the Gamow-Teller occurs at higher A. This is driven by either the electron and neutrino either being parallel, which they will be the 1, or anti-parallel, in which they can be a 0 state.
All transitions between states where the spin change is 0 or 1 and no parity change have allowed spectral shapes. Not all these transitions have similar FT values, however. We did show a table where there were differences for allowed transitions that were either allowed or super allowed. That's the genesis of these differences. Some of these relate to low Z beta emitters or mirror nuclei, but the assumption of approximately equal matrix elements between the initial and final state values for all transitions where the change of the spin is 0 or 1 without parity change is not 100% true.
When a transition from initial to final state cannot take place through this S-wave transition, we get orbital angular momenta other than 0. So these L values are going to be associated with a given transition. They're going to be first forbidden, second forbidden, third forbidden, fourth forbidden type of transitions. We've gone through how we could actually use our FT values, something related to spectral shapes with the Kurie plots, to see if the transitions are going to be allowed or not. If you remember when we calculated the logft value for the beta decay of bismuth 213, it fell in this value for first forbidden transitions. What we see with some of these trends, the degree of forbiddenness is actually related to whether or not we have a spin change, so this delta I, if it's 1 or 0, along with a
Parity change.
So if you have a spin change listed here, 1 or 0 or 2, along with a parity change, those are going to be first forbidden. If our spin change is 2 or 3 with no parity change, that's going to be second forbidden. Third forbidden,
Spin change of 3 or 4.
along with the parity change, and the fourth forbidden is listed here.
Spin change of 4 or 5 with no parity change.
As an example of this, a first forbidden transition is the decay of silver 111, where we see that we go from a 1/2 minus to a 1/2 plus. This logft value is 7.3, falls within here. Spin change 0, but there is the parity change, 1/2 minus to 1/2 plus. That'll fall into a first forbidden transition. Here's a list of radioactive isotopes with their transition classifications and the logft values. As you see, the vast majority which are allowed transitions, and then some first forbidden and very few higher forbidden transitions. Now there's also a decay effect related to electron capture, where if an electron capture occurs and it's through a K-shell vacancy is formed and it's filled by an L electron, when that L electron goes down, there can be an X-ray emitted, or there can be other processes to de-excite that nucleus. One is the emission of Auger electrons. So these are outer atomic electrons that will be emitted with the kinetic energy equal to the characteristic X-ray minus its binding energy. There's a term, the fluorescence yield, is the fraction of vacancies that are filled with an accompanying X-ray. The reason that this is important, that sometimes these Auger electrons can be used in radiopharmaceutical applications, where if you have an isotope that has a high degree of Auger electron emission, you can use this as a therapeutic agent for cancer treatment. In closing out beta decay, we'll add one more beta decay method, the double beta decay. In this case, an isotope will emit 2 beta particles simultaneously during its decay. These tend to have very long half-life. Examples are listed here: the tellurium 130, selenium 82, germanium 76, molybdenum 100 also goes through this route. And that's what's seen here. This germanium, if it went through a single beta decay, would have to gain energy. It can lose energy if it skips this arsenic step and goes straight to the selenium. Now these have very long half-life, and it's also possible to have neutrino-less double beta decay, where either the neutrinos annihilate each other or they're absorbed by a nucleon. Now another branch of beta decay is a beta delayed decay. So nuclei far from stability can populate unbound states that lead to direct nucleon emission. And what this is, where you have a beta decay which is followed by neutron emission, so a beta delayed neutron. These are important for nuclear reactors. About 1% of the neutrons that are produced in fission are actually these beta delayed neutron emission. And we'll discuss this more when we talk about fission.
This lecture covered a number of models used to describe beta decay. We went over those models, and what you should really take away from those models is an understanding of how data can be used to describe some properties related to the beta decay or the isotopes that are undergoing beta decay. You should be able to describe the fundamentals of beta decay, either beta minus, beta plus, or electron capture, and how each decay changes the neutron or proton properties in a nucleus. Remember, for beta decay, the total number of neutrons and protons remain the same, but with beta minus, a neutron is converted into a proton, and for positron decay and electron capture, an excess proton is converted into a neutron. You should be able to understand and discuss the neutrino hypothesis and how Fermi came up with the idea of the neutrino based upon an evaluation of the data related to beta decay. You should be able to understand something about spectral shapes, what influences these spectral shapes, how are particles and potentials related. You should be able to identify a Kurie plot and understand what's the difference between a straight and curved line. You should be able to look at some calculations for beta decay rate constants and understand the selection rules, particularly this logft values, how we can calculate logft's, and how do those values compare to the spin and parity of the parent and daughter states. This is probably one of the more primary sections of this lecture, where the behavior of beta decay is really driven by differences between the spin and parity of the parent state and the spin and parity of the daughter state. Remember, the decay can occur to an excited nuclear state of the daughter, which is one route for gamma emission. And you should be able to identify and explore and understand other types of beta decay, such as double beta decay. Questions that you should be able to answer based upon the lecture are provided here. One is, in beta decay, what is the correlation between decay energy and half-life? In alpha decay, we discussed and showed that a higher alpha decay energy correlates with a shorter half-life. We see the same sort of trend with beta decay, higher energy, shorter half-life. However, we see a stronger influence on spin and parity change. We even discussed whether or not a transition can be super allowed, first, second, or third forbidden. We talked about how that forbiddenness or allowedness is related to whether or not there's spin changes and parity changes. We also discussed how one could evaluate these transition types in terms of logft. The higher the logft value, the more forbidden the transition is. Again, the larger the spin changes, you tend to have more forbidden transitions. And transitions that incur a parity change tend to be forbidden, and they're odd forbidden, so first and third, if we had fifth, etc. What is the basis for the theory of the neutrino emission in beta decay? So this was developed by Enrico Fermi. There are 4 properties of the neutrino that account for beta decay. One is that the neutrino should have no charge. For instance, if we have a neutron going to a proton and an electron, this is charge balance. The particle that's produced, the neutrino, the little neutral particle, should have no charge. The particle should also have small mass. We see that the electron energy in beta decay goes all the way up to the Q value, so since there's 2 particles that are emitted, one of the particles can have all the energy. If there's another particle that comes out of this continuum, for instance the electron and the antineutrino, the energy would need to account for the mass of the antineutrino, and since the electron can go all the way up to the Q value, you could say, well, the neutrino should have no mass to account for the fact that the electron can consume all the energy even though another particle is being produced. The particle should also be an antiparticle. For instance, the neutrino, when we talk about the neutrino in beta decay, we're actually really talking about the antineutrino. If we have a proton and an electron produced, we need to produce an antimatter particle. That's the antineutrino. Conversely, if we talk about positron decay, where positron, which is antimatter, is produced, the neutrino is matter, so we talk about that's actually the neutrino. And also, this neutrino should have a spin of 1/2 and obey Fermi statistics. Since a transition where a neutron going to a proton plus an electron is not spin balanced, there's need for another fermion to account for a spin of 1/2 and balance the equation. So in beta decay, what are the two possible arrangements of spin? And basically what we're saying is, what are the spin properties of the resulting particles? Well, we talk about an electron and a neutrino. Both have spin 1/2. We just discussed this. If they're parallel, the overall spin change is 1. And if they're anti-parallel, the overall spin change is 0. So we can have this alignment that creates two possible spins. The 0 is Fermi spin, while the 1, where they're parallel arrangement and the spin is 1, that's Gamow-Teller. Fermi spins tend to dominate at low A numbers, and Gamow-Teller at higher A numbers. Other questions? For example, if we looked at a decay scheme, you should be able to understand why there are certain transitions. As an example, why is there no beta decay to the 2+ level in cerium 144? We see the decay of cerium 144 here. It's even 0+ state. It goes to either a ground state or an excited state of the daughter. And we see that it does not go to this 2+ state. Well, if we have 0+, it can either go to the 0- with just a parity change, or 1 spin change with a parity change. So going to that 2+ state is not particularly allowed. So again, we have the 0+ going to spin change of 0, spin change of 1, as opposed to a state with a spin change of 2. Okay, what is the difference in positron and electron emission spectra? A great example is shown here with copper 64. We see that the beta- particle, the overall energy is less than the positron. This has to do with the particle charge and the particle charge interaction with the nuclear charge. Fundamentally, the positron, positive, gets repelled by the positive charge of the nucleus and has more energy as it leaves the nucleus. What is Fermi's golden rule? Well, Fermi's golden rule is a model which is used to treat beta decay. It's used to evaluate the half-life of beta decay, and it's just it's shown here, the equation. We have some constants. We have a density function here. Then we have this matrix. And this matrix, it treats beta decay as a transition from an initial to a final state. And this is your mixing matrix here to describe the decay constant, which is log2 divided by the half-life. And this coupling constant here describes the initial and final states. The stronger you have a coupling between the initial and final decay state, the shorter the half-life. Another interesting property of beta decay is the fundamental force that drives beta decay. Beta decay is an example of the weak force. There are 4 forces in nature. We discussed this in the first lecture. I'm certain you've had it in previous classes. Gravity, electromagnetic, weak force, which an example is beta decay. And those weak force where we have an example, a nucleon, a neutron going to a proton. So this is beta- decay. And you can imagine that on a subatomic level, here's a neutron which is composed of 2 down and an up quark. And during this decay, this down quark converts to an up quark, converting the neutron into a proton. That's an example of the weak force. And the strong force we'll discuss, or we've had discussed a little bit when we talked about nuclear properties. It's the force that keeps the nuclei together. We'll talk about this in a little bit more detail in the course. So what is the basis of Fermi's model for beta decay? It actually exploits some of this force. It's based upon electromagnetic theory for light emission. So Fermi took that fundamental theory, applied it to the weak force, to this beta decay,
where he came up with something which describes populating certain energy densities is equal to some constants, the wave function of the electron, the wave function of the neutrino, this mixing matrix, and this Fermi constant, which he fundamentally replaced from the electromagnetic theory. So this was a fundamental equation brought in from another primary force, electromagnetic force, that was used to describe beta decay. And we discussed previously in the lecture an example question on how this matrix is used to determine the decay constant. And a final question is some applications of beta decay. How is positron decay used in medical applications? Well, it's used, it's in imaging by positron emission tomography. For example, fluorine-18 is used when a positron is produced, when it collides with, this is antimatter, when it collides with electron matter, it creates two gamma particles 180 degrees away from each other. These gamma particles each have the energy is related to the mass of the electron and the positron, so it's 511 keV. They come off at 180 degrees. If this emission occurs in a system of detectors in which spatial resolution can be achieved, you can produce a 3D image. For instance, this is used fluorine-18 glucose is used to image the brain. If people are interested in understanding properties of the brain, or if there are lesions or other impacts on the brain that they want to study and related to sugar uptake, they can use labeled molecules with fluorine-18 to produce images that are based on positron emission tomography.
When you have completed this lecture, please comment on the blog and respond to the Lecture 5 quiz. As a review, the information that you should take out of this lecture is that beta decay really describes three different types of beta decay: beta minus, beta plus, also called positron decay, and electron capture. We did review how Q values are calculated for beta decay routes, and you should be able to calculate the Q value for beta decay. You should be able to identify where on the chart of the nuclides beta decay isotopes occur and which types of beta decays occur. For instance, whether an isotope is neutron rich or neutron poor. If it's neutron rich, has excess neutrons, that neutron is going to tend to decay by beta minus, because that neutron will be converted into a proton and it'll move up the periodic table. If it's a light isotope, if it's neutron poor, it'll tend to decay by positron emission or electron capture. And there are a few isotopes that can decay by both routes. You should be able to understand and utilize the neutrino hypothesis, explain how the neutrino hypothesis came, and what were the parameters that led to it. You should understand spin in beta decay, how changes in spin and parity impact the beta decay routes, and probabilities of those decay. You should be able to use comparative half-lives in that equation that shows values for comparative half-lives. You should be able to assign transitions based upon those values, or the changes in spin and parity and those transitions. You should also be able to discuss the existence of other beta decay modes, for example, double beta decay. Now, there are a few models that were presented in this lecture showing the weak nuclear interaction relationship in beta decay. You should understand the concepts that were described in these models, but you won't be responsible for using the models to perform calculations.